Jai Janendra, Namaste and welcome to my channel. Today we are going to solve the 102nd question of the problem solving series and the 12th question of the topic tree. The difficulty level for this question is medium and this question has been asked in Google, Amazon, Microsoft, Apple, Adobe and Meta and many other companies. Balanced binary tree. So what is a balanced binary tree? A binary tree whose left subtree and right subtree height difference is not more than 1. Those trees are balanced binary tree. So in the previous videos questions we have solved height of a binary tree, diameter of a binary tree. We have found them. Now we need to find whether the tree which is given to us, is it a balanced binary tree or not. So here you can see for this node, its left subtree height is 2, right? 1, 2. Its right subtree height is 1. Okay, so this is 2 and this is 1. What is the difference? The absolute difference between left subtree and right subtree is 1, which is okay. But if it was more than 1, this tree would not have been balanced binary tree. Now, we need to check it for all the left subtrees and all the nodes, right? So for this one, it is balanced. But for this one, is it balanced? What is the height of the left subtree for this 9? 1, this one 1. So it is 0. So it is balanced for this one. This is the leaf node, so they don't have any height. This is also a leaf node, so it won't have any height. So overall, this is a balanced binary tree, so we return true. Let's look at the second example. Here, for this one, what is the height of the left subtree? Left subtree height is 3. And what is the height of the right subtree? 1. 3 minus 1, 2. So the height difference is more than 1, so it is not a balanced binary tree. I hope you have understood this question. Do was the AVL type data tree. What is AVL data tree and how can we rotate it to make it a balanced binary tree? Those are the theory things you should know. So you should watch those things. I hope you know them. Anyways, let's solve this question. How do we find out whether the binary tree is balanced, right? So now you see we found the height of the left height of the subtree, right? And the right height of the subtree, we compared it. So simple, if you know, I think you know how to find the height of the tree. If you don't know, please watch the 90-second video, I think, where I taught how to find the height of the binary tree. So I will not quote the height of the binary tree problem solution for now. So just you know what we have done here, we'll just do the same thing, okay? So we have found the height of the left subtree and the right subtree for all the nodes, and we need to compare for all the nodes. Does it meet the condition that the absolute difference between the left height and the right height is not greater than 1? And if it is meeting the condition, then we need to check it for the other left nodes and the right nodes as well, right? For all of the nodes, whether it is a valid thing or not, and if for anything it is not valid, we'll return false. So like for example, if this one, if we see, so we can say, firstly we can write it root equal to none. You don't need to write the whole code, just return true, because it would be a balanced binary tree, right? If there is no node, the left height and the right height of the subtrees are 0. Otherwise, what do you do? We find the left height. Int LH is equal to, say, height, we give the root left. Okay, so this height function we have already discussed, height of the binary tree, how to find it. Here we give this height, root right. Okay, we find the height. Now if the absolute difference between this left height and the right height, if it is less than 1 and less than equal to 1, and if the other nodes are balanced, we check for root left and we check for root right. Okay, so if this condition matches, so again it would do for the left, right? Is it balanced or not, right? And also for the root right. If for all of them it is balanced and the absolute difference is less than equal to 1, for all other cases also, we will return true. Otherwise, we will return false. As simple as that. Okay. So this will give us a solution. Okay. This will Yeah, but is it an optimal solution? No, it's not an optimal solution. Why? What is the time complexity? Find the height order of n. And now again we go to the left and the right. Right, we need to find for the left. We will call this function for the root left, and again it will find the height. So for every time if it finds the height, so n into n. So order of n square. So can we optimize it? We saw in the question diameter of binary tree. How did we optimize it from n square to n? But in that case, with the height of the binary tree, we found the diameter because already we have calculated that, right? When we find the height of this by the bottom up approach, already we have height of the left subtree for this one, this one, this one. Okay, and we use that diameter logic between that function of the height. But here, this condition, can we use this condition here while just finding the height of the tree once? Okay, can we use this condition in the middle so that we'll get the answer instead of finding the height of all the nodes separately? So let's try what we can do. This is an order n square solution. Let's rub this. Okay. And now let's call a function return height. Okay, root. We pass root. Okay, let's see. Now we know how to find the height of the binary tree. Okay, tree node district root. Okay, right. So what do we do in the beginning? We find the, if root is equal to null, we return 0, right? Because the height is 0, then return 0. Otherwise what we do? We find the left height int LH is equal to height of root left. Okay. We find the right height of root right. Okay, done. Now we have the height, and then we can return the height here as 1 plus max of LH and RH, right? It will give us the height, and we have given this height, but we need to return either 0 or -1. So if we write the condition here that okay, if absolute difference between LH and RH, if it is greater than 1, then there is an issue, and this will be called every time height root left. Also every time this would be checked, LH and RH value would be different. So whenever we see that this is greater than 1, we return something which cannot be returned. What is the minimum height of a binary tree? 0 if it root is null. So let's return -10, -100, anything. But if I return -1 say, and here if it is written height is not equal to -1, if it is equal to any other value, we are okay. So if it is not equal to -1, that means this condition would be true. Suppose the height of the binary tree in this case is 3. So 3 is not equal to -1, which is true. So finally it would be true, it would be balanced. But here we check this condition that okay, when we find the height of the binary tree, we got the left height, right height in any while traversing this, because here also we are going left, right. Okay, once only we are going. So it is order of n. You might think that okay, here also we are going here, so it would be order. No, for this one we are going once only. But when we did the first question, for here again you go left and right. Okay, so this is order of n only. I hope you have understood what I mean to say. Anyways, so now we have added this condition. So when we are finding this LH, so while finding only LH height for root left, this condition might arise, right? So for again LH, this height will call again LH RH. So this condition would arise, and LH might be a -1 value. So we have to write if LH is equal to minus 1, right? Then return minus 1. Okay, because same goes for RH also. Okay, so if RH equal to minus 1, return minus 1, and this will help us to solve the problem in order of n time complexity. Let's try run this code for this example and everything would be clear. Okay, so we get 1, okay, and now we run this code for this 1. We find the height of this, this is not null, so we find the left height, okay, left height for this one. This will again call the left height for this one. This will again call the left height for this one. Okay, at the end, since its left height is 0, 0 would be returned. Okay, this has 0, the right height also it would be 0. So finally, what would be the height for this one? 1 plus max of 0, 0, 1. Okay, so this left height is 1. Okay, for this LH would be 1, and for this RH also would be 1. Since both are not equal to minus 1, so we will not fall into this condition. We will also not fall into this condition because the difference between them is 0, not greater than 1. So we will get this 1 plus max of LH RH, which would be 1 plus max of LH RH, both are 1, so it would be 2. So we will get the left height of 2 as 2, and we will get the right height of 2 as 1. Okay, so now we have got 2 and 1 for this 2. Okay, and both LH and RH are not equal to minus 1, so we go here. What is the difference between the left height of 2 and the right height of 2? The difference is 1. Okay, 2 minus 1, 1, which is not greater than 1. So this is not, this is balanced till here. Okay, so we return the final actual height. What is the actual height? 1 plus max LH RH. So the left height is 2, that is greater than 1. So 2 plus 1, 3. So this whole height is 3, which would be the return for 1. So for 1, LH is 3. Okay, and what would be the RH for 1? RH would be 1. For no, so for 1, this actual root, we got the left height as 3, right height as 1. Now we see, okay, this is not coming minus 1, okay. So we see the difference because LH is 3 and RH is 1. Now the difference is 3 minus 1, 2, absolute difference. So 2 is greater than 1. So here for this tree we have understood this node, the tree is not balanced. Okay, so minus 1 would be returned instead of this actual height, which is 4. Okay, if this was not there, then 1 plus max of LHRS 3, max of 3, 1 is 3. So 1 plus 3, 4, which is the actual code of the height of the binary tree. But here this condition will make it return minus 1. That means it is not a balanced binary tree, and we check here. Since it is minus 1, if it is minus 1, then it is false. Minus 1 not equal to minus 1 is false. That means it is not a balanced binary tree. Okay, it's balanced. So in this way, we can solve this problem in order of n time complexity. The link to the question is given in the description. Please try it yourself and then come to my code walkthrough section. Here is the code walkthrough of the 102nd question of the problem solving series and the 12th question of the topic tree in the LeetCode platform. Balanced binary tree. You can see the companies that have asked these questions are this. Okay, and let's look at the code. This is the order of n time complexity code, but before this, let's look at the order of n square time complexity, which I've already submitted before. So where we find the left height and the right height, and we can check this condition if it is true, and we check for root left and root right balanced or not, and if all of them are true, then we return true, otherwise we return false whenever we encounter anything which is not balanced. And this time complexity, as we discussed, here we are finding that this is the height of the binary tree code. So we are finding the height, and we see, okay, if it is not balanced here, this would be order n. And again, for left everything, it would be order n, so automatically it would be order of n square. So we have a better solution where we do it in order of n, and this is that solution. We call this function height of the binary tree, and we see this if it is not equal to 1. So already I have explained this. We find this left height if it is not equal to minus 1, if it is equal to -1, we return -1, so that you know why we do this. And this is the main condition, and then we return as the height. Anything height anywhere, no issue, but if it is -1, we can understand that this condition will fail and it would return false. Okay, so let's submit this. So you can see it has passed. And yeah, see you soon in the next video, where I'll be explaining the 103rd question of the problem solving series and the 13th question of the topic tree. Jai Jinendra.